Hello, welcome to the lecture number 25 of the course Quantum Mechanics and Molecular Spectroscopy. Towards the end of the last lecture, we were looking at the transition moment integral, which is nothing but f mu dot E I. Okay. Now, we wrote that mu as an expansion of mu naught plus alpha r plus beta r square plus gamma r cube plus etc. Okay. This is a Taylor series expansion. Around the equilibrium geometry. Therefore, your TMI will now become f mu naught plus alpha r plus beta r square plus gamma r cube plus etc. dot epsilon dot I. Okay, where alpha is nothing but d mu by dr evaluated to r naught, and beta is nothing but half d square mu by dr square evaluated at r naught, and gamma will be nothing but 1 over 6 d square mu d cube mu by dr cube evaluated at r naught. Okay. These are the coefficients. Okay. So, this is nothing but dipole moment derivative Okay. We will come to the usage of dipole moment derivative later in this course. Okay. Now, in this case what mu naught is called permanent dipole moment, which is nothing but the dipole moment at the when the molecule is at equilibrium geometry. So, simply for example, if you have a molecule AB, okay, because of the electronegativity difference, if there is a partial charge q plus on A and q minus on B, and this distance is r, okay, r naught, that is the equilibrium geometry, then your mu naught will be nothing but equal to q times r naught. Okay. Now, one of the interesting thing that you will still need in the time to evaluate in your transition moment integral, when you write TMI, this is equal to f mu dot epsilon I, is the fact that we still have to evaluate the initial and final wave functions. In the beginning of the course or throughout the course up till now, what we have assumed that we have a Hamiltonian H naught, we still do not know what that exactly is, into I is equal to EI I and H naught F is equal to EF F. So, this we have assumed all while, but we still do not know what is H naught precisely. Okay. Now, what I am going to do is that let us start with a very simple problem, that is the rotational state. So, what we look at is pure rotational spectra. Okay. We will look at the pure rotational spectra. Okay. Now, if you take the total, if you have a molecule AB, okay, then and this is your R naught, okay, one can write a Hamiltonian H is equal to minus h bar square by 2m A del square A minus h bar square by 2m B del square B plus U REL AB. Okay. Now, one can write such a Hamiltonian H. Okay. Now, this is what, this is the kinetic energy of atom A, and this is nothing but kinetic energy of atom B, and this is the relative or bond energy of AB. Okay. So, we will go back to the same thing. So, your H is minus h bar square by 2 m A del square A minus h bar square by 2 m B del square B plus U REL AB. Now, what does U REL AB consist of? If U REL B will consist of, okay, it will consist of 3 terms. One is electron nucleus attraction, 2 consists of electron repulsion, 3 nuclear repulsion, and 4 because of electron kinetic energy. Okay. Now, I want to make one approximation called rigid rotor approximation. Now, what am I saying when I say rigid rotor approximation? Very simply, it means the following: if I have A and B and they are separated by distance r naught, okay, the distance is fixed. That means the nuclei are no longer moving. Okay. So, the nuclei are at the fixed positions in this case. Okay. When you have such a scenario, then the sum of U REL AB will be equal to a constant. Okay. So, the nuclei are fixed, and in the AB molecule the nuclei are fixed, they are not vibrating, they are not anything, they are just fixed. Okay. When such are fixed, when the 2 nuclei are fixed, then okay, electron nucleus attraction will not change, the electron repulsion will not change, the nuclear repulsion will not change, electron kinetic energy will not, all of them will be some constant numbers, and when you add all the 4 constant, you will get one more constant. So, your U relative AB will be equal to constant. So, which means your Hamiltonian HRR, okay, RR because rigid rotor, okay, I will call rigid rotor as RR, okay, HRR will be now be equal to minus h bar square by 2 m A del square A minus h bar square by 2 mb del square b, okay, plus some constant. Okay. Now, one of the interesting things of energy measurements is that you can always measure energy with respect to some value. Okay. For example, in thermodynamics we only measure delta G's, and that is delta G's because we always think that the delta G of the standard states is 0, okay, and we measure delta G with respect to a standard state. Similarly, in this case one can think that one can measure energy with respect to this constant, which is nothing but U relative AB. Okay. So, when I am measuring with respect to this constant, I can ignore it. So, my H RR will be now be equal to minus h bar square by 2 m A del square A minus h bar square by 2 m B del square B. There was a constant which I ignored because I am measuring energy with respect to that. So, this is my Hamiltonian. Okay. Now, if you think of it, so what I have is the following. Okay. I have A and A is connected to B by a stick that has length R0 and that is not changing. That is what I said, rigid rotor. Okay. So, the positions of A and B are fixed. Okay. Now, let us for a time being think that what all the possible motions that this particular system can undergo. Okay. Now, I told you the R0 is fixed. Okay. So, when the R0 is fixed, it can only undergo two motions. One is that if you have A and B, okay, attached, okay, by R0, then of course it can move along x, say z direction, it can move along x direction and it can move along the y direction. So, the whole molecule can move in some direction, okay, along x, y and z. Okay. Now, what else can it do? Because A and B cannot move, then what can it do? It can rotate. AB can rotate like that without changing the distance, or it can rotate like this. Okay. So, AB can rotate and AB can translate. So, only possible motions are translation and rotation. Okay. Now, what did I say? So, we had this Hamiltonian which was nothing but H, okay, is equal to minus h bar square by 2 m A del square A minus h bar square by 2 m B del square B. Okay, now we had two of them. So, there are two possible motions, one is the motion of A atom and other is motion of atom B. However, they are stuck to each other. So, A and B cannot move independently. So, in that scenario this equation can be written as minus h bar square by 2 capital M del square Cm plus minus h bar square by 2 mu del square internal. Okay. So, this is something is called coordinate transformation. Okay. I will not go to the mathematics of it, but I will tell you what. So, if I have a quantity A and B, okay, that is my body A and B. So, what you have is the coordinates of A and B, okay, and there is a mass of it, which is MA, and the mass of this is MB, and there are some coordinates, okay, and what I will call it as RA and RB. So, the center of mass will lie somewhere here. So, this is center of mass, okay. So, this will have R center of mass. Similarly, you have another distance called this as R naught, which is nothing but R internal. So, there are two things that one can do is that instead of having RA and RB, there are the vectors from the origin going to A and B. There are two vectors that are representing this system, RA and RB. Instead of that, you could choose an alternate description, that is R center of mass and R naught. So, it is an equivalent description of it, and one can do the math. Okay. There is something called center of mass transformation. Okay. One can look it up in some textbooks, okay, and it will clean found out that one can make such a transformation in the Hamiltonian without making any approximations. But there is only one thing that I need to define, where your M, capital M, is equal to MA plus MB, okay, and small mu is MA MB divided by MA plus MB, and this is called reduced mass, and this is total mass. Okay. Now, these two Hamiltonians, so HRR equals to minus h bar square by 2 MA del square A minus h bar square by 2 MB del square B is identically equal to minus h bar square by 2 M del square center of mass minus h bar square by 2 mu del square internal. Okay. So, instead of having two coordinates representing A and B, now you have an alternate description in terms of coordinates representing center of mass and the internal motion. Okay. And this is of course valid only when these are valid under this. Okay. Now, there are two things that let us go to the Hamiltonian HRR equals to minus h bar square by 2 M del square center of mass minus h bar square by 2 mu del square internal. Okay. Now, there is one issue is the following, is that this quantity is the center of mass motion, that means the whole object is moving. Okay. So, this is nothing but your so you can now calculate your HRR as two quantities, one is H center of mass plus another is H internal, where H center of mass is equal to minus h bar square by 2 M del square center of mass. So, this represents the motion of the or Ke of the entire AB molecule. Okay. Now this is just a motion of the entire AB molecule in some direction x, y, z or a linear combination thereof. So this essentially leads to what, and there is no potential acting on it. So essentially this leads to what is known as free particle. Okay, and we know the free particle is unquantized. Okay. So one can think of having a this one as HCm chi Cm is equal to okay, E Cm chi Cm, where E is equal to h bar square k square by 2m is the minus h bar square k square by 2m, that is the kinetic energy. Okay. So we do not have to worry about the Hamiltonian corresponding to center of mass, because that just represents the motion of the entire AB. Okay. And just if you want to move a particle or a mass or a AB molecule, okay, of course it is not related to any spectroscopic transition. So we will not worry about it anymore in this course. Okay. Now what we are left with is the remaining part, H internal, which is nothing but minus h bar square by 2 mu del square internal. Now if I had a particle AB, okay, and this one was at XA, YA, ZA, these are the coordinates of A, and XB, YB, ZB as internal coordinates of or coordinates of B, then you can write X is equal to XA minus XB, Y is equal to YA minus YB, Z is equal to ZA minus ZB, and this represents internal . Therefore, your del square internal will be equal to d square by dx square plus d square by dy square plus d square by dz square. Okay? And this is the internal coordinates. Okay. There is of course one problem. Okay. Now the problem is this, is that when you want to, so I know I told you that AB is a rigid body. Okay. And of course you must remember R naught will be equal to x square plus y square plus z square to the power of half, which will be nothing but xa minus xb whole square plus ya minus yb whole square plus za minus zb whole square to the power of half. Okay. Now there is one thing that I told you, is that of course this can move in the xyz direction, the entire molecule AB. But I told you that we are not concerned with such a motion because it does not lead to any spectroscopic transitions. Okay. Now the thing that we are interested is in the rotational motion, either in the plane of the board that I am writing or a plane that is perpendicular to the plane of the board. Okay. When you have such motion, then you are talking about a motion of AB in a circular fashion. So that means you can think of your H internal your H internal is equal to minus h bar square by 2m del square internal, and this internal motion is the motion of the molecule without moving the center of mass. So, what is this? This is that this is motion that does not change the center of mass. Okay. So, you have to keep your center of mass fixed and then move around. Okay. So, you have to rotate the body either in the plane of the board. Okay. So, A, B can rotate, okay, or rotate perpendicular to the plane of the board, okay, while keeping its center of mass fixed, because the motion, if there is a motion with of the center of mass, that has already gone into the other Hamiltonian of the free particle that I discussed little bit earlier. Okay. So, now what we are concerned is just the motion of this AB molecule in such a way that its center of mass remains exactly in the same position. So, this will lead to rotation. So, your H internal, okay, this is equal to minus h bar square by 2m del square internal, which is nothing but minus h bar square by 2m d square by dx square plus d square by dy square plus d square by dz square. This should represent rotation without changing the center of mass. Okay. We will stop here and continue in the next class. Thank you.